Thank you very much for the invitation. It's a great honor to be invited to speak in this seminar. And yeah, as you know, I'm an analytic number theorist. And what I'm going to do today is to show how spectral geometry and analytic number theory can interact in a very interesting way. And I want to show what analytic number theory has to offer to questions of spectral geometry. I'll try, I know that most of the audience are not analytic number theorists, so I will try to give a smooth and soft introduction into these methods. Okay, let me start with a cliche. Can you hear the shape of a drum? So what do we want? We have a compact Riemann surface, we call it X, and we consider the eigenvalue problem delta F. Delta is the Laplace operator equals lambda F, so we are interested in the spectrum. And the question is, what properties of X can we get out of the distribution of the eigenvalues? What properties can we hear? What part of the geometry can we recover from the spectrum? And well, for instance, we see the area, we see the length of the boundary if there is a boundary. So there are certain parts of the geometry that we can obviously read off from the eigenvalues. And the question that I want to ask today is, can we also hear dynamics? Is it possible to say something on the geodesic flow if we know the statistical distribution of the eigenvalues? So in particular, can we decide whether the geodesic flow is regular, which for me just means if you have two trajectories that are close to each other, well, how do they develop? Do they remain relatively close, or is it chaotic and they diverge exponentially quickly? All right, there is a major and famous conjecture. If the system is regular, then the eigenvalues should be Poisson distributed. This is a conjecture of Berry and Tabor, and more precisely, what do I mean? I rescale the eigenvalues so that the mean spacing is 1. You could say I normalize the area to be 4 pi. And then Poisson distribution means the probability that a randomly chosen interval x plus r, so an interval of length r, contains precisely k eigenvalues, is r to the k divided by e to the r times k factorial. That is the conjecture. So the conjecture means you should be able to recover the fact that the system is regular by looking at the eigenvalues, namely if they are Poisson distributed, then it should be regular. Now, this is a physicist's conjecture, so it should be taken with some care. It's more like a moral conjecture. But it gives some connection between the spectrum of X and the geometry of X. All right, we have no chance of proving this conjecture, even in special cases. There seems to be no hope to prove rigorously general results in this direction. Nevertheless, it's a good motivation. And so we are modest and start with a very simple case. And the setup for today is the case of flat tori. So these are the Riemann surfaces that we are going to look at. These are maybe the simplest cases, but well, nevertheless, maybe we can say something. So we take a lattice in R2, and our Riemann surface is the quotient, the Euclidean plane modulo the lattice, and the eigenvalues are simply exponentials coming from the dual lattice. Okay, and so we can compute the eigenvalues completely explicitly. We take elements in the dual lattice, take their norm squared, multiply by 4 pi, and that's the spectrum. And the key point is, because these are norms of lattice points, they are given by a quadratic form with integer arguments. Yeah, the lattice provides some integral structure, and so the spectrum is parametrized by some quadratic form whose coefficients depend on the lattice. It's easy to compute them if you want, but we don't need to. It's just some coefficients, and it's an integral quadratic form. No, it's a random quadratic form, but it's with integral variables. Okay, so that's our spectrum, and the big advantage in this case is, of course, that we can compute the spectrum completely explicitly. There is an obvious symmetry. The values mn give the same eigenvalue as minus m minus n, so we desymmetrize this, and then we would expect to have multiplicity 1. Okay, and here's the first piece of warning. If we take the most obvious lattice of the integers, then the dual lattice is the same, and so the spectrum is contained in 4 pi z. In particular, the distribution is obviously not Poisson, because, I mean, it's in a lattice, there is some rigidity. This is obviously not Poisson distributed. The gaps are at least 4 pi, and yeah, so in this case, the Berry-Tabor conjecture is clearly wrong. So we have already our first counterexample. And of course, you can generalize this, this counterexample. You can just take a rational quadratic form. If you take a fixed rational quadratic form, you have the same problem. In fact, you even have the problem when the quadratic form is close to something rational. So the coefficients could even be irrational, but if they are something like Liouville numbers, so maybe you're familiar with this concept, this could be a number whose decimal digits are always 0, except at the factorials, there is a 1. A number like this is so close to something rational that you, in effect, cannot distinguish it from a rational number. And even for such coefficients, the distribution of the values of this quadratic form is certainly not Poisson. So you have to take some care, and you have to exclude the obvious counterexamples. And you see already it's not even clear what is obvious. Okay, so what is known? The first progress was made something like 25 years ago by Peter Sarnak, and he showed that almost all tori satisfy Poisson pair correlation. So not the whole Poisson statistics, but the pair correlation is Poisson. If you close your eyes and pick randomly a lattice, then the pair correlation should be Poisson. And this was made deterministic in an Arnold's paper of Eskin, Margulis, and Moses, and they showed that all tori that are far enough away from things like rational quadratic forms satisfy pair correlation. So this badly approximable can be made completely precise. So let's say the coefficients are something like square root of 2 and square root of 3, then the pair correlation is Poisson. So this is a deterministic result. Okay, that is all basically that's known. And yeah, just for fun, here's a numerical example. We take the quadratic form where E is Euler's number 2.7, m squared plus E n squared. Here is the list of the first eigenvalues. And here is a kind of histogram where I plotted the eigenvalues. And you see there are from time to time some bigger gaps. So around 100, you see here in the list 92, and then the next eigenvalue is at 98. So there is a considerable gap here. But then, for instance, around here, like 120, you have 124.46, 124.49. So they can also cluster a bit. And this looks sufficiently random. I mean, this picture looks like if I play darts just randomly. Yeah, that is what we would roughly expect to be a Poisson distribution. Okay, I'm now coming to my own results. And let me start with triple correlation. So remember, what was known before was the pair correlation due to Sarnak and in a deterministic way due to Eskin, Margulis, and Moses. And so the next thing you might want to look at is the triple correlation. And so what is this? So we take a coefficient vector, so we fix our lattice basically. Each alpha corresponds to a quadratic form, and so to a lattice. We fix two intervals I and j, and we look at triples of eigenvalues within the first n eigenvalues, such that the I second minus the I first eigenvalue are in the interval I, and the I third minus the I first interval eigenvalue are in the interval j, and I want that they are all distinct, so they are three distinct indices. And the number of such triples renormalized by 1 over n is the triple correlation. Okay, and the first theorem that I want to present, which is joined with Eisleitner and Radziwill, says, well, it gives an asymptotic formula for the triple correlation, but not for an individual lattice, but on average over a region of lattices. So you average over lattices, and the expected triple correlation would be the length of I times the length of j, and this is averaged over a set of lattices of measure r. So it does give the expected triple correlation as n goes to infinity, but not individually, but only on average. And in some sense, in a weak average sense. I mean, it's not an L2 mean or something like that. It's just the average. Okay, nevertheless, it's the first statement on a triple correlation, which is, of course, a bit harder than pair correlation. Okay, what can you do with this? As such, it looks a bit technical. Here are some consequences. The first consequence is very simple. It means that for almost all lattices, so for a full Lebesgue measure set of lattices, the triple correlation, the lim inf, cannot be bigger than the expected value, and the lim sup cannot be smaller than the expected value. Okay. And by the way, of course, we cannot ask this for all alpha. The best we can hope for is a statement for almost all alpha, because we know already it's wrong if we have a rational quadratic form. So in some sense, the best we can hope for is an almost all statement. And this bounds the lim inf from above and the lim sup from below. This is just some set theory and follows pretty easily from theorem 1. The more interesting corollary is on long gaps. Now, this is a difficult story anyway. If you have a Poisson distribution, we will talk about this in a moment, and we expect it to be Poisson, then we expect that very short gaps can occur, but long gaps are very hard to detect and they occur very rarely. I mean, Poisson means it's very random, and this is like getting papers to referee. You get them randomly, and it happens very rarely that there is a long gap between the next referee request, but it happens very often that you get 2 papers in a row and need to referee them immediately, one after the other. So long gaps are always much harder to detect, and they happen very rarely. And so what can we say? We can say the following: for almost all lattices, there are infinitely many gaps that are g times as long as the average gap. And of course, what is g? Now, g is this. G is essentially 2. So, but it's a little bigger than 2, and this is important. So there are infinitely many gaps that are at least twice as long as the average gap, and a little more than twice as long as the average gap. And this G is a solution of a complicated algebraic equation that, so it has no closed form, but numerically it's 2.006. Okay, why is this relevant? it is relevant that it's bigger than 2. So this is a non-trivial result, because one can show that there exist sequences with Poisson pair correlation where all gaps are at most twice the average gap. Yeah? So if I prove that there is a long gap, there is a gap like 1.5 times as long as the average gap, then this could just follow from pair correlation. Maybe maybe this is just a trivial consequence of pair correlation. The fact that we have something more than 2 means that we cannot conclude it just from pair correlation. There must be an extra input, because pair correlation alone could mean that all the gaps are at most twice the average gap. And so this is really a conclusion or a consequence of triple correlation, that we can go beyond 2. Okay, but it's still a fixed constant. We are unable to show, and to my knowledge, this is an open problem. So this is an interesting open problem. Show that, well, show that there exist interesting tori, so irrational tori, that have infinitely long gaps in their spectrum, like arbitrarily long gaps, unbounded in terms of the average gap. This is not known, and so the best we can say, it's twice as long, and a little more than that, twice as long as the average gap. Okay, this is what you can conclude by a combinatorial argument once you know the triple correlation, at least on average. All right. What I really want to talk about, other questions?
Yeah, I mean, I have one.
Yeah.
So do you know if increasing this G would mean that you lose this property for almost all alpha, or would it even be possible to increase G and still be true for almost all alpha in terms of
we know nothing. I have no idea how to increase G even for a single alpha.
Yeah, but it could be possible that increasing it destroys it for at least a measure for some.
Oh, probably not. Okay, I mean, I would probably not. I would conjecture that for almost all alpha, so we have to throw out the obvious counterexamples. But if there is Poisson distribution, then we would expect that there are unbounded gaps. So G should go to infinity. That's what we would expect for almost all alpha.
Okay.
We are just unable to prove it. So this is an interesting open problem, and I think, I mean, there are lots of things. I mean, you can ask for the quadruple correlation, and you can, I mean, there's lots of things you can play with. And I will not say much about the methods that go in this result. But there are some methods on the market, but as of now, they are not strong enough to make big progress in this direction. So this is certainly, these are interesting questions. All right, so this was just the appetizer. What I really want to talk about are small gaps. How close can two eigenvalues be? How small can the gaps be? And what would we expect? So if the eigenvalues are completely random, Poisson, then the pair correlation, which I wrote down here, for a given interval I, should be, of course, the length of I. I mean, if they are randomly distributed, then you have n squared choices for I1 and I2. You divide by n, and the probability that you land in I is just mu of I. But this should not only hold for fixed I. For fixed I, this is Sarnak's result, at least for almost all alpha. But this should be true uniformly all the way down for an interval of length 1 over n, essentially. And that's the smallest range you can ask for, because if you go below that, then you don't expect, I mean, you expect this set to be empty. Yeah. If mu of I is less than 1 over n, then this T2 is less than 1 over n, and this means that the set is essentially empty. So you cannot ask for anything better than that. But the smallest scale at which you would expect small gaps is 1 over n. So that is what you would expect. So in particular, there should be gaps as small as 1 over n among the first n eigenvalues. And that's the so-called birthday paradox. So if you have 25 people in your class, 25 students, then the probability that, then the birthdays should be randomly distributed, and the probability that you get a clash, that you have two birthdays that are very close together, like if n is the number of students in your class, it's like 1 over n. Yeah? So that's what you would expect. And this little o of n is like a plus minus epsilon, and I don't want to be too precise about that, at least for now. But nevertheless, let's do some fine-tuning. And there is a result of Devoir, which says that if you have a true Poisson sequence, then the minimal gap is almost surely infinitely often bigger than log n over n, but almost surely less than log n squared over n for almost all n. Yeah, so yeah, there is a little bit of wiggle room in this 1 over n, but that's roughly of a log scale. That would be if you have a true Poisson sequence, and we want to find out if our sequence of eigenvalues satisfies this. Okay, here are the results. First of all, for almost all alpha, we have the correct pair correlation. So this interval has length delta, and the value is delta, all the way down to the Planck scale. All right? But there is still an epsilon uncertainty, but if you're not so strict with epsilons, then it goes all the way down, as low as it can possibly be. And this remains true in the smaller subset of rectangular tori. So if my lattice is a rectangular lattice, the same statement holds. Almost all rectangular tori satisfy this. Secondly, for almost all rectangular tori, the smallest gap among the first n eigenvalues is bigger than 1 over n times a log power. Remember, Devoir said it's on a log scale. Here, it's a log power. So infinitely often, it's bigger than 1 over n times a log power, where c is a funny constant. C is that constant, 0.08, which was recently improved to 2c in a recent preprint. And then there are some, so this is the only deterministic result. Theorem 4 is the only deterministic result that I'm going to present. If you pick a very special rectangular torus, that's the square of the golden mean, but also for some other values, the smallest gap among the first n eigenvalues is O of 1 over n. And this has been extended to all, I have to be a little careful. So if you extend this to all quadratic irrationalities, then you have to give a 1 plus epsilon here. By Dan Carmen, a student of Zeev Rudnick. But the interesting point is that here you're really at 1 over n on the nose, which again violates Devoir because he says there should be a log n. So on a very small scale, there seem to be some arithmetic features that slightly violate Poisson. Okay, these are the results, and now I want to present, we go into number theory, and I want to present some ideas of what goes into the proofs and how, this is maybe the moral of the story, how arithmetic enters this spectral geometry question. Okay, and here's the basic idea, which is so basic that it's really high school arithmetic. Let me just focus on rectangular tori for simplicity. So my quadratic form, so these are my eigenvalues. Yeah, x and y run through integers, alpha is a random number, and I want to know something about the distribution of these numbers. They give me the eigenvalues. Okay, and how can I detect small gaps? Well, if I have one eigenvalue and I subtract another one, then I can simply write it in this form. Yeah, just open the squares and open the differences of the squares and write it in this way. And you see, if this difference is small, it basically means that this blue parenthesis is small. And this means that alpha is very close to a rational number where both numerator and denominator is factorizable in a certain way. Both numerator and denominator have product shape with two factors that are roughly of size square root n. Yeah, that's all. Once I find such a Diophantine approximation of alpha, I find a small gap. Yeah? So the Diophantine properties of alpha determine whether I find small gaps. And I can make this quantitative and count them. That's the basic arithmetic idea, which is really very down to earth. But making this into a proof is not so down to earth. Okay, let's recall the theorems 2, 3, and 4. Theorem 2 is the generic one. That's the hardest one that I will discuss at the end. This shows that there are sometimes biggish small gaps, and this is a deterministic result. And I will start by proving theorem 3 and 4, which are both rather easy. So here is some fun stuff based on multiplication tables. So we go to primary school, and if you write down the multiplication table for like 1 by 1, 5 by 5, and 3 by 3, up to 10 by 10, the question is how many numbers come up in this multiplication table? And we'll see how this enters in a moment. So for a given alpha, we denote by delta alpha of n, the smallest gap among the first n eigenvalues. And I look at the set of all alpha where this is less than 1 over x. I want the measure of this set, and I introduce a second set, namely those alpha where the distance of a multiple of alpha, namely the qth multiple of alpha, is bounded in this way. And then it's easy to see that the measure of sxq is 2 over x, basically because multiplication by q is measure preserving. Okay, now, if I have an alpha whose smallest gap is 1 over x, then I know I find a small gap. That's 1 over x. So I find values x1, x2, y1, y2 up to square root n, such that this difference of the two eigenvalues is bounded by 1 over x. But this means if I factorize this and I factorize, I mean, this is obviously, this is an integer. So it means there is a multiple of alpha that's close to an integer. And so I factorize this into y1 minus y2 and y2 plus y2. And so this alpha must be such that u times v, the multiple u times v of alpha, is very close to an integer, namely by a difference 1 over x. Okay? So this means all these alphas are in such a set. So it means that Sxn is contained in the union of all those. Okay, and now I simply compute the measure by counting how many products uv do I have. So how many numbers come up in the multiplication table up to square root n? How many products do I have in the multiplication table of size square root n? Oh, there is a factor 2 missing because there is a 2 here. Well, never mind. And this is something you can compute. In fact, Kevin Ford computed this for us. That's bounded by n over some log power of n. And that's precisely the funny constant c, 0.08, that comes up. So if I choose x to be that, then this part of the fraction cancels, and I get something that goes to 0. And then it's easy to show that almost all alpha must have a smallest gap that's bigger than that. Well, the opposite, so log n to the power c over n. Okay, so that's that. That's the complete proof. once you have this input, this multiplication table input, then you're done. And this shows that some arithmetic can violate, at least on a small scale, Poisson distribution. So, fun stuff too, Fibonacci numbers. So again, a little bit of recreational mathematics. We take the square of the golden mean, and we look at the continued fraction expansion. And as you may remember, the continued fraction expansion of the golden mean are the Fibonacci numbers, and the square of the golden mean also has Fibonacci numbers in the continued fraction expansion. So Fn is the nth Fibonacci number, which is essentially the nth power of the golden mean. And we have this approximation. And now we remember that in order to get a small gap, we want to factorize these. And now we use properties of Fibonacci numbers. The GCD, if this is the index, the GCD of n and m, this Fibonacci number is just the GCD of those Fibonacci numbers. And so this means in particular, if n is even, then Fn is divisible by Fn over 2. And so there is a cofactor, let's call it Gn over 2. And so I can simply write Fn is Fn over 2 times Gn over 2, and the same with Fn plus 2. And here is my difference, and I can write these factors as differences of squares, and that's all I need to do. And so I find my small gap. So this comes by direct construction using properties of Fibonacci numbers. And this argument works more generally for all quadratic irrationalities, not only the golden mean, but this is much more subtle and much harder. It needs cyclotomic polynomials and some algebraic number theory. So then you need some more serious number theory if you want to show this for all quadratic irrationalities. But this can be done. All right. So, as I said in advance, I want to show you some number theoretic methods, how you can use number theory for spectral geometry. And now comes the point where we really dive into analytic number theory. I try to make it not too technical, but I want to show you some ideas how you can prove theorem 2. And just to remember, theorem 2 was pair correlation all the way down to the Planck scale. Yeah, a completely uniform pair correlation, which implies in particular small gaps. Okay, so we want to show pair correlation all the way down to intervals of length. I rename delta, so the length is now 1 over n times delta, and I allow delta to grow very slowly. Okay, and as we said, it suffices to count rational approximations of alpha, where numerator and denominator are both divisible in a certain way, and the difference is bounded by 1 over m, where m is the size of n squared divided by, well, basically divided by the length of the interval. That's what I need to do. I need to count quadruples of integers that satisfy this. Okay, how do you count? Well, you sum over all possible choices of n1, n2, n3, and 4. And it's much better to count in a smooth way. Yeah, so W is a fixed smooth bump function. We want to do Fourier analysis, so we cannot afford sharp cutoffs. We want a smooth count. And if alpha is very close to this fraction, then the logarithm of alpha is very close to the logarithm of that. And basically, I need to count something like this, where W is a fixed smooth weight function. And I do some Fourier analysis. So I apply the Fourier transform to W. And well, what I get is just this sum. This is just Fourier inversion. And you want to evaluate this. Okay? And morally, what you would expect, that the main term for this integral is for small y, because if y is big, there should be lots of oscillation in this sum and in this exponential. And if there is lots of oscillation, it should be small. So the big contribution should be close to 0 when there is no oscillation at all. Okay? And this means, well, if there is no oscillation, then I have an integral of size, well, y is small, so it's essentially bounded. I have a 1 over m here, and I have 4 copies of square root n. So I get square root n over m, which is by definition just delta, as I expect.
I'm sorry.
Yeah.
It might be me who's slow right now, but where's the in discounting? Where's the log coming from?
Oh, this is just my choice. I rewrite this by taking logarithms. If
okay,
alpha,
so you take...
this is just for convenience. It's easier to write it that way. Mm-hmm. Yeah. If alpha is close to something, because the logarithm close to 0, I mean, like the logarithm is essentially linear, and so I mean, if alpha is close to that, then log alpha is close to log of that. That's all I'm doing.
Okay, so in a way, it's additional smoothing both on the W, but also using logarithm too.
Correct.
Okay.
Yeah. That's one way of looking at it. Yes. So this is just my design to make it simpler to work with. All right. Now, of course, as we said before, we cannot ask for an individual result. For individual alpha, this must, I mean, it's clear that I cannot prove anything because there are counterexamples. I want an almost all result, and an almost all result means I need to bound a second moment. Yeah. So I take the rest. Oops. There should be full screen. Sorry. So back to full screen. Yeah. So I take the rest where y is large. This should be the error term. And I estimate the error term on average over beta, where for convenience, I write beta instead of log alpha. So I rename log alpha is now beta. And I take the remaining stuff where y is large, and I want to make this small, on average over beta, not individually, but on average. And I want a power saving. The main term is delta, and I want a power saving for the error term on average. Okay, that's my goal, and I just copied this here. I squared it out, and that's what I need to show. That's the same display as before. All right, what can we do? Well, first of all, we need to integrate over beta. That's our key tool, because that's the extra average. So we open everything, integrate over beta, and this means, so I get 2 copies of y if I square this out, y1 and y2, and beta is fixed, so it means that y1 and y2 must be close together, otherwise there is a lot of oscillation that kills the entire integral. So without loss of generality, y1 minus y2 is bounded by 1. And then I'm left with 1 copy of this sum and another copy of this sum. And since y1 and y2 are essentially the same, by Cauchy-Schwarz, it's almost the same as taking an 8th moment. I don't lose anything substantial here by assuming that y1 equals y2, in fact. So this is the guy I need to bound. All right. Now you see there is some heavy arithmetic because there is a sum. So this is a Dirichlet polynomial here, and we need to evaluate the 8th moment of a certain Dirichlet polynomial. Okay, and here is a little bit of core analytic number theory. So how can we estimate the 8th moment of such a Dirichlet polynomial? Well, there is something called large CIF, which I'm not going to explain. I just tell you that this is a very general method that works for arbitrary Dirichlet polynomials, and it gives a generic bound integration length, which is m, times square root of the summation length. I have 8 copies of n to the 1/2. This gives n to the 4, so the square root is n squared, and again, the square root of the summation length. Okay, I'm not going to tell you how you prove this, but it's not difficult, and it's a very general soft approach that doesn't need much arithmetic. Okay, and if I use this, then, okay, I have a 1 over m squared in front of it. I have this. And if I just plug this in and use that m equals n square over delta, I get this. And you see, you lose, because you want delta squared times n to the minus something, but you only get delta squared. So this is not enough. You don't get a power saving. So this approach is not strong enough. And of course, it's not strong enough because it's generic. It doesn't use any arithmetic. The second approach uses the Riemann zeta function. And the basic idea is that this n sum here is some portion of the Riemann zeta function. And you can write this by some standard integral transform as an integral over the Riemann zeta function. That's essentially this n sum here. Okay, and you integrate over the real part of size 2, and the imaginary part is essentially bounded. Okay, you shift the contour to 1/2. That's the critical line for the Riemann zeta function when the real part is right at 1/2 on the critical line. And this would give you roughly, if you plug in 1/2 here, you get 1/4 to the power 8 gives n squared over m squared times the integral over the Riemann zeta function. All right. Now, what do we know about the Riemann zeta function? Okay, what would we expect? We would expect that the Riemann zeta function is essentially bounded on the half line. That's what we expect, but we can't prove it. What we know is the second moment is essentially of size t. The fourth moment is essentially of size t. And that's 100 years old. And that's where the story ends. So if you're not an analytic number theorist, you may say, oh, you poor guys, within 100 years, you haven't made any progress. Yes, we haven't made any progress. So we know a little bit more. So Heath Brown showed something for the 12th moment, but that's not optimal. It's t squared and not t. The integral is of size t, or the length is of size t, but the value is t squared. And that's all we know. So in particular, we don't have the 8th moment available. We only have the 2nd and the 4th moment. If we had the Riemann hypothesis, which we all believe, but we don't know, the Riemann hypothesis would apply t to the 1 plus epsilon for all moments. So if we are willing to assume the Riemann hypothesis conditionally on the Riemann hypothesis, we can just prove bound the 8th moment by m. So we get n squared over m, and that's delta. And we want to bound, so we want, yeah, so that is okay if delta is something, is just a little bigger than 1, then we can choose eta appropriately to make this work. And I think, yeah, I put the inequality signs in the wrong order. I want an upper bound for this. Yeah, so the delta square should be on the other side. Anyway, so here we only get delta, and the target is delta squared minus a bit. So if delta grows a little bit, then we are good. Okay, but this is conditional on the Riemann hypothesis. And so we would like to remove the Riemann hypothesis because we want an argument that is not dependent on the Riemann hypothesis. And the idea is, so remember that we had 2 approaches. One was based on the large sieve, and this barely failed. And the second approach was on the Riemann zeta function, but then we need RH. And now we combine both. And the idea is the 4 variables are further decomposed into products where one factor is very short and the other factor is relatively long. And so the same argument gives me an 8th power of the short guy and an 8th power of the long guy. And for the, I don't touch the long guy to start with. And for the short guy, I shift the contour of the Riemann zeta function to 1 minus delta. And then I need to estimate this guy here. So I promise this is the last technical slide. And the deep input that we can use is that very close to the one line, we have relatively strong bounds in the direction of the Riemann hypothesis. We can bound zeta of sigma plus it by t to something. So if sigma is close to 1, this is very small, and I have a power here that's bigger than 1. That's the key tool. And that's a deep input from the 1960s that uses all the analytic number theory machinery. Now, if we have this available, we can use the large sieve for the second factor and this bound for the first factor. And so what I get is this bound for this moment of the Riemann zeta function. T goes up to m. And so I have 1 to the delta to the power 3 over 2. And I use the large sieve for the second factor, integration length, square root of summation, square root of summation. I rearrange this. I just multiply it out. You can believe me that this is what you get. And both terms are acceptable. Remember, n squared over m is delta. I forget the minus 2 delta. I just drop it. And then I'm left with 4 kappa, and m is roughly n squared. So I get 16 delta to the 3 over 2 coming from this. But that's fine. If kappa and delta are sufficiently small, then I'm good because my target is delta squared. If I only have a delta, I can afford a small power of n. Now here I have delta squared, but now I have 8 delta minus kappa plus 2 square root of delta. And you see the 3 over 2 translates into a 1/2 here. And now if I choose delta small enough, given kappa, I can choose delta small enough so that this remains negative. And so I save a little bit. Okay? This is how analytic number theorists think. Okay? So this is a bit of a tricky game with exponents. And really the deep input is some knowledge on the Riemann zeta function close to the one line. And this helps us win. All right, this is still not the end of the story. This argument produces the existence of small gaps, but it does not produce an asymptotic formula for the number of small gaps because our count is not correct. We cheated. We both overcount and undercount. Not every number does have such a factorization, but if it does have such a factorization, it may not be unique. So there is both an overcount and an undercount, and this argument would not give an asymptotic formula. It only gives the existence. This thing is harmless because it's true that not every number does have such a factorization, but almost every number does. And the ones who don't, we don't need to care about. This is really a small error term. This is the much more serious obstacle that such a number may have many of such factorizations. And so the way out of this is to consider special factorizations where one of them is a prime. So not just arbitrary products, but products where one of the factors, namely the small one, is a prime. In this case, the factorization is essentially unique. And for technical reasons, and again, you see we are within analytic number theory, we need that the prime is of a certain order of magnitude. Okay, don't worry about this. And one can show that indeed most numbers have such a factorization and it is unique. Now you need to run the whole argument, but not with arbitrary r's, but with primes in this interval. And again, you need all the analytic number theory machinery. And this is based on work of Matthieu-Radziwill in the Annals that uses properties of certain Dirichlet series over primes to make the argument work. All right, I'm not going to go into any further details. Let me just summarize what I tried to explain today. We started with flat tori simply because I can write down the spectrum explicitly. I can write down the eigenvalues totally explicitly. And they have some number theoretic significance. This enables us to show Poisson distribution, at least on a broad scale. And if I look on a fine scale, Poisson is violated. As we have seen, multiplication tables, Fibonacci numbers, there are small arithmetic features that violate Poisson on a small scale. And the moral of the story is that number theoretic methods can be used to shed some light on problems in spectral geometry. Okay, that's it. Thank you very much for your attention. And that's the end of the talk.
Thank you very much for the talk. We have time for questions now. So if you have questions, please just unmute yourself and go ahead.
So I have a question to start with. So presumably, so you mentioned that at some point that it would, at least in principle, be possible to look at this problem for say quadruple correlation or higher moments. Is there any other obstruction appearing than the fact that you will have to deal with higher moments of the zeta function and longer factorizations than two terms?
Okay, the triple correlation uses a different argument, and this cannot be translated into the Riemann zeta function. This uses a genuine Diophantine argument that has nothing to do with the Riemann zeta function, simply for the reason that triple correlation depends on two equations. The nice thing about pair correlation is that there is only one equation that you can easily encode into the Riemann zeta function. As soon as you have two equations, or even more than two equations, things become much more difficult. And then you have systems of equations. And I don't know how to encode this in the Riemann zeta function alone. So this needs a different argument that I didn't talk at all about today. The machinery that we developed for triple correlation applies in principle to any correlation, except that it becomes so complicated that we don't know how to solve it. So the technical obstacles become so overwhelming, and the counting problems, basically you need to count lattice points in very cuspidal regions, very strangely shaped regions. And just my tools don't suffice to do this in general. Yeah, so there is hope that this will be doable one day. And I mean, in principle, we have some tools available, but it becomes very, very hard.
Yes. Thank you.
May I ask a question?
Yes.
Yeah, I come from the old school of quantum chaos. And there, it was quite helpful to consider not the two-point correlation function, but to look at its Fourier transform. And then, for example, in a Poisson, then the Fourier transform is just a straight, it is just one constant. And my question is whether this kind of an approach, where you look, for example, at short intervals, then this corresponds to long time, then the properties of long periodic orbits on your torus starts to play a role, and then you would like to look at correlations between long periodic orbits. They give you the deviation from the Poisson. So I don't know how to do it, and I never thought about it, but it is at least in quantum chaos, that was one of the means to connect, the classical dynamics to the quantum dynamics. Here, the classical dynamics is quite simple. It's just a motion. So I don't advise you to take it. I wonder if anybody tried it.
That's an excellent comment, and I don't know either. I mean, the fact that, I mean, the Fourier transform plays a major role is, I think, was obvious in the talk, and also the things that I did not talk about, they all use the Fourier transform. I mean, the first thing you do whenever you start is you Fourier transform this. All these counting problems, also the ones that I didn't talk about, step number one is always Fourier transform it. But what you're saying is that maybe some dynamics and some dynamical arguments can be used. And this would be very interesting. I didn't try it, and I don't know if anyone tried it, but it's certainly something that one should keep in mind.
Thank you.
Thank you for the question and for the answer. Anyone else wants to comment or ask something? I think there are no further questions. So let's thank our speaker again. Thank you very much, Valentin.
Thank you for having me.